So let's talk about a reaction that alkanes can participate in that we haven't looked at yet in any other session. So this reaction is called halogenation. So remembering back to our early lectures, halogens are actually in group number 7 of the periodic table, which is shown as VII. So this means that they have 7 valence electrons. So they're quite close to a noble gas, quite close to being stable. They just need one extra electron. So the best known halogens in this group are things like chlorine, Cl, fluorine, F, or bromine, Br. So we're going to see each of these in this session. So a halogenation reaction occurs when an alkane is going to be reacting with a molecule of the halogen. So halogens are often seen in pairs like this, Cl2, because of the way their electrons are arranged. So if we draw out the Lewis dot plot of our chlorine here, it's actually got 7 valence electrons because it belongs to group 7. So I've got 6 there, and then there's going to be one orbital with a single electron. So if we have 2 of these chlorines side by side, then each of them will have one missing electron. So what could these chlorine atoms do to stabilize themselves and have the electron octet of 8 electrons? We can actually form a covalent bond where the 2 unpaired electrons are being shared. So when we have Cl2, what it actually is 2 chlorine atoms that are covalent bonded by a single bond, and we summarize that as Cl2. So exactly the same thing happens with our fluorine, F2, because it also needs one extra valence electron to be stable to achieve that electron octet. Do we know any other atoms that have a single valence electron needed to be stable? Hydrogen does the same thing, but remember hydrogen only has one electron because it's only got one electron shell. So all hydrogen needs is another hydrogen to form a covalent bond with, or another atom like carbon, and that makes it stable. So essentially, what we can see in this reaction of halogenation is we can actually substitute hydrogen atoms for the halogen atoms because they have this very similar property of only needing one covalent bond. So in the reaction down here, we can see that in the reaction, one of the alkane's hydrogens is actually going to be replaced with a halogen atom. And in the process of doing this, we're going to create an alkane that is now halogenated. It contains a halogen atom. So the methane in this case is reacting with a chlorine molecule in the presence of heat and light. So it corresponds to quite a large energy input. So remember, energy is needed to begin chemical reactions. For this particular one, we need quite a lot of energy. And as this occurs, one of the hydrogens within the methane is actually being replaced with a chlorine. So let's have a look at how this works in a little bit more detail. So we have this key characteristic of the halogenation reaction where the alkane's hydrogen atom is being replaced by one halogen atom. Okay, so we're getting this direct switch. Hydrogen out, halogen in. So I've highlighted the one in red that's going to be moving. So we have methane here with a carbon and then 4 single bonds to hydrogen. We're reacting it with a halogen molecule. So remember, before you can get a chemical reaction to take place, we need an energy input to break some of the existing chemical bonds. So the chemical bonds that are going to break are the one between the 2 chlorine atoms and the one between the carbon and the hydrogen. Essentially, now that they're broken, we can get this atom rearrangement. And then that then leads to the formation of new covalent bonds, and then we'll have different products as a result. So what's going to happen is this hydrogen atom is going to come over and associate with one of the chlorine atoms. And that means this other chlorine atom in green here can actually come and associate with the carbon. And we can see the end result of that is that the chlorine now forms a new bond to the carbon atom. So it's actually replaced the initial hydrogen that was there. What happened to the hydrogen atom? Well, it came over and formed a new bond to chlorine. So we've actually made HCl, hydrochloric acid, very strong acid in this process. But the thing we're focusing on is the halogenated alkane. So essentially, through this halogenation reaction, every time we do this, we can replace one hydrogen with one halogen atom. So based on this, would you be able to turn our methane into something that looks like this, where we've got carbon bonded to, say, 4 chlorine atoms? Would that be possible? It would be possible, but we'd need to do 4 separate halogenation reactions, because remember, each reaction is only going to replace one hydrogen. So if we want to replace 4 hydrogens, we need to do this reaction 4 times. So that's what we can see, the point down the bottom here. Additional hydrogens can be substituted by performing the halogenation reaction again. Alright, so now we've got a short animation to show how this actually occurs. So we're starting off with our reactants. On the left we have methane, and on the right we've got our halogen molecule. So the first thing that happens is we have an energy input, which is going to break some of the initial covalent bonds within the reactants. And now that we've got that breakage happening, we saw that rearrangement. So as soon as the covalent bond is broken, we can see that the atoms are now free to move about. And what happens is the chlorine and hydrogen actually switch positions. And once they've switched positions, we then get the formation of these new covalent bonds. And that results in the formation of our products. So now instead of methane, we've got our halogenated alkane, and our other product is hydrochloric acid, HCl. So let's look at that once more. So we're starting off with our reactants, bond breakage with energy input, and then atom rearrangement, and then finally bond formation, and that is the final step that allows us to have our new products, which are the halogenated alkane and also the hydrochloric acid. So let's have a look at an example of where these halogenated alkanes have actually been used. So halogenated alkanes that have a lot of halogen atoms added have this name of CFCs, chlorofluorocarbons. So some of you might have heard of CFCs because they actually used to be used as refrigerants. So they would actually power the pump within a fridge to actually keep it cool. So it's providing the energy to keep our fridges cool. However, it was found that 2 of the CFCs that we've got pictures of here, Freon 11 and Freon 12, were actually very bad for the atmosphere. It was actually destroying the ozone layer. So for that reason, they've actually been banned at around 1987 that occurred. And you can see the use of these CFCs has actually declined sharply since that point. So the damage is already done in a sense because the ozone layer can't be rebuilt, but at least the ozone layer that still remains isn't going to be severely affected by these CFCs that we've stopped using. At least the vast majority of countries have. So if we look at these CFC compounds, we've got a carbon in the center, and then we've got 4 halogen atoms arranged around the outside. So to go from our methane, that is CH4, to one of these CFC compounds, what type of reaction would that require? Well, we'd need to do the halogenation. And how many of these halogenation reactions would we need to achieve this? We'd need 4 separate reactions, because remember, each halogenation reaction is going to only replace one hydrogen with one halogen atom. So because these CFC compounds have all 4 positions substituted, that means they would have needed to do 4 halogenation reactions to make this possible. Alright, so question to consider now. How many halogenation reactions would it take to convert methane into a halogenated alkane that contains 3 fluorine atoms? So to make this a little bit easier, I'll draw a structure for you. Okay, so we've got a halogenated alkane looking like that with 1 hydrogen and 3 fluorines, and it tells us that we started with methane, which is a CH4. So now would be a great time to pause the recording and have a go at working out how many halogenation reactions it takes to go from our methane to the structure we see on the right hand side here. So to work this out, we need to understand that one halogenation reaction equals 1 hydrogen to fluorine. In this case, it could be chlorine, switch. And if we look at the top structure here, we can see that there's 3 positions that have switched from hydrogen to fluorine. So for one halogenation reaction, you get 1 switch. So that means for 3 halogenation reactions, you're actually going to get 3 switches to fluorine. So the correct answer here is 3 halogenation reactions for that reason. So the next thing we're going to have a look at is an alkyl group. So essentially an alkane, for example, methane or ethane or propane, can actually lose one of its hydrogen atoms, and by doing this it becomes one of these alkyl groups. So the significance of an alkyl group is that because it's lost one of its hydrogen atoms, it can actually attach to something else, because it's got a spare bonding position, which we can see on the right hand side here. Once the methane compound in this case has lost one of its hydrogen atoms, it's now got this spare position where it can bond to something else. Remember, the carbon atom always has to have 4 covalent bonds to be stable, so the alkyl group will try and attach to something else. So for naming our alkyl groups, we just replace ane at the end of the name with YL. So that means methane becomes methyl, ethane would become ethyl, and so on. So let's have a look at what we can use these alkyl groups for. So essentially the key characteristics of the alkyl groups is that it can attach to something else. It's got a spare bonding position, so it can bond to something else. This can be an atom or a group of atoms in a compound that it might be able to form a covalent bond to. So you can think of the alkyl group as having an R, because the R represents an attachment point to a single atom or a group of atoms, just like we saw for our alcohol functional group. So that means our CH3 here, which is a methyl group, can actually bond to lots of different combinations of atoms as represented by this R. So let's have a look at an example of this. So here we have a 5-carbon chain. So if we go from left to right, so we've got 1, 2, 3, 4, 5 carbons. And branching off this 5-carbon chain is a CH3. And what is CH3? Well, that's a methyl group. So the R group in this case is actually the 5-carbon chain. So this part here is the R that our methyl group has attached to. So you can see another example here where a slightly longer alkyl group is attached to that 5-carbon chain. So again, the 5-carbon chain here would be considered the R group, so the connection to another group of atoms. And then we've also got the ethyl group here, which is a CH3, CH2. So normally ethane would be CH3, CH3. So we've got those two connected to each other. But by the ethane losing one of its hydrogen atoms, it becomes CH3, CH2. And because the second carbon here only has 2 hydrogens attached, it means it's got a spare bonding position. So it can actually attach to something else. And that something else is represented as the R. So we can see that in this structure here. The CH2 within the ethyl group here can attach to the rest of the compound here. So in the box above here, we've got some of the common alkyl groups. We've had a look at the methyl group and the ethyl group, which are derived from methane and ethane respectively. You can also have a propyl group. This time we've got 3 carbons that attach to an atom or group of atoms as represented by the R group here. Alright, so let's practice this a little bit. So we're going to try and find the alkyl group in this compound below. So to do this, try and identify the longest chain of carbons first. So that'll be your R group. And then the shorter chain of carbons will actually be your alkyl group. To name the alkyl group, you'll need to consider how many carbons are actually in that group. Is it 1, 2, or 3? And we can use that nomenclature that we looked at earlier. So if it's 7 carbon atoms, that corresponds to hept. So you can look back at this on the table if you like. But that wasn't really what we were trying to identify here. Once we've identified that R group, we're looking what it's connected to. And that is this 3-carbon chain down the bottom here, which is actually an alkyl group. So because it's a 3-carbon alkyl group, we designate that as prop for 3. So that will be the propyl group. So we've identified the propyl group as being the part down the bottom here. Alright, so we've reached the point in the session now where you can have a go at the first 3 revision questions. So remember, you can access these via the LMS. So in the revision quiz, the first 3 questions correspond to what we've done so far in the lecture. So please have a go at these questions to try and cement your learning. It'll help you a lot, and it'll also help you build your understanding into the next part of the session. So have a go at those first 3 questions now. Alright, so let's have a look at the summary for this part of the session. So we had a look at the difference between our saturated and unsaturated hydrocarbons and their functional groups. So the saturated hydrocarbons only contain single carbon-to-carbon bonds, meaning they had a maximum number of attachments to hydrogen, therefore being saturated with hydrogen. And this was true for our pseudo-functional groups like alkane and cycloalkane that contained only single carbon-to-carbon bonds. Whereas the unsaturated hydrocarbons had double or triple carbon-to-carbon bonds, which meant that there was less positions available to bond to hydrogen, meaning they were not saturated with hydrogen, hence the unsaturated term. And this corresponded to things like our alkenes, cycloalkenes, but also alkynes with a triple carbon-carbon bond, and also the cycloalkynes. We then had a look at some of the properties of our alkanes. The fact that the alkanes are non-polar compounds, meaning they won't dissolve in the polar water. The alkanes were able to burn in oxygen via combustion reactions, which are also redox reactions. And we also saw that the alkanes could react with halogen atoms to replace the hydrogen atoms via a single halogenation. So every time we do that halogenation reaction, replacing one hydrogen atom with one halogen atom. And we saw that this could be used to make those compounds like the CFCs, where we had a carbon attached to a combination of chlorines and fluorines instead of the hydrogen atoms. So the alkyl groups, what we just looked at, can be derived from our alkanes. So once the alkane has lost one of its hydrogens, essentially that is when it becomes the alkyl group, which can bond to another atom or a group of atoms. So we had a look at how we could identify the alkyl groups based on the number of carbons present and their position within a compound by finding the smaller part of the carbon chain which branched off the large part. So we saw also that methane becomes the methyl group, so that's the naming nomenclature when the alkane is converted to the alkyl group.